So these 3 points that I can see everybody writing down are sort of the main idea of the chapter on evolution. The first point is the idea about change over time. So one of the things that we'll discuss in this chapter is that populations, and I really want to highlight the word population. One of the things I think that is a misconception is that if we're saying evolution is happening, we're saying an organism is going to change over time. And that's one of the things that I'm absolutely not going to say, that an organism changes over time. We're going to talk about populations. That means we're going to look at an entire group and which type of organisms make up the group. They change, and they change over time. So none of the processes that we're going to discuss here are particularly fast. Most of them take a long time, years, hundreds of years for them to be visible. And we're going to talk about a couple of types of changes. Changes that are visible. And by visible, I don't just mean things that you can see that are physical characteristics, but maybe things about behavior or actions as well. But we'll also talk about genetic code, which isn't something that you can see, but it's something that we can analyze. What we're going to try to do in this chapter is to explain the unity, which means the possibility of common ancestors, as well as the diversity, the idea of speciation, so new species forming, of life. So we're going to talk about the fact that there are common things among species, but that there are, of course, different species, and how did that come about. And finally, we will spend quite a bit of time going over the scientific evidence that will support this. Now, I'm highlighting this because there are a lot of ideas out there about evolution and how much of it is true and is not true, and what do you believe and what do you not believe. And so maybe one of the things I'll say first, and we will discuss an article about this a little bit later, is that the Catholic Church is not opposed to the concept of evolution. So you can be Catholic and you can think that evolution happened. They're not diametrically opposed to each other. So we're going to start in this thing about evolution by talking about how ideas have changed over time, by highlighting a few of the maybe key people involved. So are these all the people who have ever said anything about evolution? Of course not. I'm just going to highlight a few points in time, a few historical perspectives that maybe might help show you where the ideas came from and how the ideas have changed. So if I start over 2,000 years ago, so if you look at the time frame here, BC, or as I should probably more correctly say, BCE. Does anybody know what the letters stand for in the time thing? Yes. Yeah, the BCE means before the Common Era. In the past, when we used to just say BC, it really was referring to Christ, and then people decided they didn't want Jesus to be the determining factor for when the years were calculated. It's not me. I have no comment on that. But just so you know, BC and BCE mean essentially the same thing. So where 0 is, that would be when Jesus was born. So we're talking over 2,000 years ago, in the time when guys like Aristotle and Plato and other Greek philosophers were around. What kind of ideas did they have? Well, the general idea that was sort of prevalent amongst all of the learned people was that organisms were created perfectly. In other words, there was no evolution. The way an organism was the way it was. If there was a new species, it just happened that way. There was no environmental selection pressure that caused the new species. So these guys talked about organisms being perfect the way that they are, meaning organisms are not changing. If there's a new species, it's just showing up. It's not an existing species changing its form. Now, one of the things that you might know, if you've heard of any of these people before in your lives, is that a lot of the ideas that people had a few thousand years ago maybe didn't turn out to be well supported now. And so this idea that organisms were perfect and that there was no evolution, or this idea of independent organisms, probably is not the most well supported idea. And then you see there's a big space of time where I didn't put anybody's name, and that's because there were a lot of years where being a philosopher, which meant researching things and studying things, was not super cool, not the thing to do, not the thing that was encouraged. And so when we jump ahead almost 2,000 years here to the Renaissance, this is where a lot of thinking was maybe more encouraged. It was a much cooler thing to do. And this is where we run into guys like Da Vinci and Galileo and Newton, where a lot of ideas that we would probably still say hold true today scientifically were discussed or discovered or at least brought into the general population as a main idea. And one of the things that I like to point out here is around this time is when people finally started to realize and probably eventually accept that the Earth was not the center of the universe. Now, does that have anything to do directly with evolution? Not really, but it's the change in idea. It's this acceptance of change. So if we're going to accept that this idea that the Earth was flat, and if you walk to the edge you would fall off, and that it couldn't be round because you would fall off the bottom because nothing would be holding you up, if we could accept that that wasn't true, then maybe it was a good time to start accepting ideas about organisms maybe not being independent of each other. So this guy, you can imagine how popular he would have been with something like a religious organization, ours included, when he said this: humans and apes have a common ancestor. He was probably a really popular guy when he was like, hey everybody, us and monkeys, yep, we have a common ancestor. It wasn't a super popular idea at first, but because we're in this sort of place where change was being accepted, you start to look at the evidence and you start to look at things that are shared characteristics and you think, huh, yeah, maybe that does make a little bit of sense. For example, I'll just give you a few things that would be sort of common between us. If you take a look at other organisms compared to humans and apes, we have a lot of physical characteristics that are the same. So if you talk about face, shape, and orientation, the fact that for us and other primates who can be on 2 feet, our face faces forward instead of our face and our stomach facing different ways because we're not walking on 4 feet. That was a pretty big thing. The idea of articulated joints would be another. So the fact that I can do this, the fact that I can do this with my fingers, So the movement and the articulation in all of the joints, these are some scientific things that are characteristics that we share with primates, but not with other organisms sort of as a whole. And there's lots of other things too. I mean, we're mammals, we give birth to live young, but there are lots of organisms that have that characteristic as well. So he came along with this idea, probably wasn't super popular right away, but as soon as the ideas started coming, then so did the studying. And that's what we really needed to help get some of these ideas off the ground, was some actual physical evidence that would support what people were saying. So the first person that we should mention is Georges Cuvier. So he's French, but he is basically credited with starting paleontology. Some people would call him the father or the grandfather of fossils. But he started the study of fossils, which is called paleontology. And there are a few things about fossils that I would want you to know. First, he reconstructed animals from fossils. So this was proof that the fossil was actually an organism in the past, because if you could reconstruct it and have it look like an organism, well, then that provided proof. The second thing was that the animals that are no longer living. So he reconstructed organisms that we did not see any of in our current life at the time he was reconstructing them. Then he noticed that each stratum, which is a layer of rock, and each stratum or layer of rock, if you look at the little picture down here, could sort of be illustrated by the difference in color, the different sections that exist. But each stratum or layer of rock didn't have the same type of fossils in it. So each stratum or layer of rock has unique fossils. And so that was very telling to him, because each layer of rock didn't have the same things, even though you might be taking the rock from the same geographical area. He found that deeper strata had older fossils. And we'll talk a little bit more about how maybe we could scientifically prove that a fossil was older. But at this point, it was generally accepted that the deeper you went with the rock, the older that the rock was. And he found evidence of species disappearing and or reappearing. He called this revolutions. Today we might call it extinction or speciation, but he noticed that a species would be in the fossil record and then all of a sudden gone, or that a species that had never been in the fossil record all of a sudden showed up. So that's providing evidence that species went extinct and that new species possibly could have formed. You'll notice that I was fairly vague with the dates here, because saying the year that something happened is not something that I would ask you ever. Maybe the person's name might be important, especially last names in science. So I would expect that you know that Cuvier is associated with fossils, for example. But there's another couple of people that we need to discuss. These are two different people, last names here, Lyle and Hutton. They used radiometric techniques to determine that the Earth was 4 to 5 billion years old. Now I've got a little illustration here that shows you what a radiometric technique is. It goes into way more detail than I would expect for you to be able to reiterate to me, but I just want you to have an idea of when we say that we're going to carbon date something, what that actually means. Now, carbon dating, first of all, let me tell you, is the butt of a ton of science jokes. One of my pictures at the back said scientists love dinosaurs so much they carbon date them, using it as the verb date instead of to say when something happened. Super hilarious. You could make lots of jokes about carbon dating. But here's the basic idea. There is more than one form of carbon. If you have taken any sort of chemistry, or if you remember Science 10 very briefly, someone may be mentioning the word isotope to you. There's more than one form of carbon. Some carbon has more neutrons in it than others, and it's called carbon-14. So there's two forms of carbon. Well, there's more, but these are the two that we're discussing. Carbon-12 is regular, normal carbon. It has 6 protons, 6 neutrons, 6 electrons. That's what it's made of. Carbon-14 still has 6 protons, still has 6 electrons, but it has 2 extra neutrons. So it makes it a little bit heavier than regular carbon. It doesn't act differently because it still has the same number of protons and electrons. So it's still just carbon. And carbon, like we saw, is part of photosynthesis and cell respiration, which means living organisms have carbon. So somewhere a living organism, in this case my little snail in a shell, absorbs carbon-14. So carbon-12 is always getting absorbed, but probably a little bit of carbon-14. Carbon-14 doesn't make you sick, it's not going to kill you, it's just a slightly different variety of carbon atoms. Eventually, the organism dies and becomes a fossil. And then you can take a sample of that fossil and figure out how much carbon-14 is there. And we can figure out how old it is from this because carbon-14, which is radiocarbon, decays at a known rate. We know how fast it takes for this type of carbon to decay, which means break apart. So if you take a piece of the fossil and you burn it, and you get carbon dioxide gas, you will get some carbon-12, which is the light blue stuff, and you will get some carbon-14, which is the dark blue stuff. Carbon-14 decays, and then you can use a radiation counter to pick up electrons. That's basically the idea. I will not ask you at any point to re-explain to me how carbon dating works. I just wanted you to have an idea of what that actually means. We're seeing how much carbon-14 there is. Anyways, using this process, they figured out that the Earth was 4 to 5 billion years old. So, what does this mean? It means what on earth happened for like a few billion years before humans started keeping records of what was going on? So the fact that they decided that the Earth was this old opened the door for the idea that something must have been going on before we were here, before we existed. And so this maybe paved the way for people to think more about evolution. It didn't necessarily prove anything about evolution directly. It just gave us a better time frame. It gave us way more years during which something could have happened, and so opened the door for talks of evolution. Does anyone want to ask anything about carbon dating? So there are some other ideas about evolution other than the ones that we will focus on. We're going to focus on the idea of natural selection, which is Charles Darwin's idea. But there are some other ideas that I do want to mention. One of them is a theory that talks about where maybe prokaryotic and eukaryotic cells came from. It's called the endosymbiotic theory. So if you think what endo means in or inside. Symbiotic means relationship. I think it's grade 7 where you talk about symbiotic relationships like mutualism, commensalism, parasitism. You might redo it again in grade 9. I don't remember anymore. But there are some other theories that help explain maybe some of the details that go along with evolution. And this is one of the ones that I like. This one shows how a prokaryotic cell looks a lot like a mitochondrion. If we take a look at the wavy membranes inside the mitochondrion that are called the cristae, and these wavy lines inside of the prokaryotic cell that are called mesosomes. Now, the prokaryotic cell itself is not part of our course, but this is a good time for you to remind yourself what a mitochondrion looks like, that the inner membranes are called cristae, maybe that the space inside of it is called the matrix. But the idea then was that perhaps, since these two things look so similar, for me to get an animal cell, I had a prokaryotic cell maybe engulf another. So if one prokaryotic cell engulfed another that kind of looks like this mitochondrion, maybe that's how I got an animal cell that could metabolize energy the way that it does. If I was to talk about a plant cell, perhaps I could use the same logic and say that my chloroplast resembles a prokaryotic cell as well. So this same prokaryotic cell could have become a chloroplast, and a plant cell was when one prokaryotic cell engulfed another, but this time it engulfed one that was more like a chloroplast than like a mitochondria. So it's just a theory, which means that we don't know for certain that this is the way that it happened, but it is a nice way to perhaps explain how we got from a very basic cell to maybe a more complex cell. And we know that cells engulf each other. It happens all the time. For example, in your immune system, cells are engulfing other cells all the time. That's how your white blood cells can help attack foreign cells. So this is another idea that would go along with the idea of evolution. Now, the last thing in my list of ideas, historical ideas, that I want to talk about in terms of evolution is the idea about whatever you want to call it, creationism, creation science, intelligent design, the idea of creationism versus evolution, because it's a very hot topic, especially in a place like this one. And there is an excellent article by a guy named Dennis Lamoureux. He taught a course that I took at the U of A about something called evolutionary creationism.